Our work, namely UniGS, focusing on sparse-view 3D reconstruction and NVS task using 3D Gaussians as 3D representation. There are several existing works focusing on sparse-view 3D reconstruction and NVS task. Most of them follow the strategy that predict 3D Gaussians for each pixel of each view under the input view's camera coordinates. The process is similar to returning each pixel a depth. Then they transform each view's inputs to world coordinates and simply merge them by point concatenation. Such design brings three main limitations. The first one is that they predict each pixel a 3D Gaussian. As the pixels are evenly distributed, the final 3D Gaussians also evenly distributed in both simple and complex regions. As shown in the figure, for example, the door on this teapot has more texture information and therefore should be represented by more 3D Gaussians, which does not appear in previous work. The second one is that the fusion of the 3D Gaussians from each view may encounter the challenge of ghosting, i.e. the predicted per pixel 3D Gaussians from different views cannot align to others after concatenation. As shown here, an extra part of the rendered object can be obviously observed at the handle and the foot part. This issue arises from that the estimated positions of 3D Gaussians in each view may be imprecise, so that the merging of 3D Gaussians cannot align well. The third limitation is that they require the same number of input views during both training and inference stages. Otherwise, their performance would notably decrease, constraining practical applications where the quantity of input views is variable, as shown in Figure C. The x-axis is the number of input view in inference, y-axis is the evaluation matrix. As shown in the figure, when the number of input view during inference is the same to training, previous models have a meaningful result, while when it comes to different number of input views, the results reduced. Considering these limitations, and inspired by our single-view model design, we define a set of 3D Gaussians in the world space unitarily no matter what the number and resolution of input views are. Similar to the design in the single-view setting, we first use a feature extractor to extract image features from multiple views and link the unitary 3D Gaussians to queries. Inside the decoder layers, we query information from the multi-view image features by projecting the unitary 3D Gaussians onto different views to iteratively update our 3D Gaussians. With such design, utilizing unitary 3D Gaussians that avoid per-pixel local optimization, this avoids the even distribution problem as the first limitation and let the model learn to allocate more 3D Gaussians to complex regions that has more texture information. It also avoids direct fusion of 3D Gaussians from each view and addresses the ghosting problem as the second limitation. To efficiently leverage multi-view image features, we introduce multi-view deformable cross-attention MVDFA global queries of first defined for the unitary 3D Gaussians within world space. The global queries undergo modulation by camera parameters for each view to derive view-specific queries, considering that the input contains multiple views, but the 3D Gaussians are defined unitarily. Specifically, the global queries are subject to a linear transformation using weights and biases derived from a multi-layer perceptron MLP conducted on the camera parameters of each view to obtain the view-specific queries. These view-specific queries are used to calculate attention score and sampling offsets. The unitary 3D Gaussians are projected onto each input view to generate projected points, serving as reference points in deformable data within each view. Subsequently, the view-specific queries are updated by deformable cross-attention with values being image features sampled surrounding the reference points for each view. Finally, global queries are updated by all view-specific queries merged through a weighted summation, where the weights are determined by an MLP operating on the view-specific queries. Therefore, our model supports arbitrary number of input views in inference without retraining and thus solves the third limitation. With the designs above, our model achieves SOTA results and the increment on all the metrics here are significant, while usually there are only less than 1 decibel increment on PSNR, while in our method here, exceeds 4 decibels. Here is the visualization on GSO dataset. Left column is the rendered novel views, and right column is the center of 3D Gaussians. The results here is given for views as input. From this visualization, our model is proved to have the ability of reconstructing high-quality 3D in both geometry of texture. Here is the in-the-wild image to 3D and text to 3D tasks. We can observe that our model can deal with different kind of tasks with the help of some off-the-shelf generation-based multi-view image models.